Hello, welcome everyone. Welcome to this faculty development program, which is a week-long faculty development program on basic skills in experimental physics. There are three elements to this faculty development program, and I'm going to talk about the first 3 days, where we are going to teach how to make, design and make PCBs. Now, why would you want to learn about making PCBs? At the end of the day, the PCBs are going to be used for fabricating electronic circuits. And in the first session of these 3 days, I'm going to show you a lot of innovative projects which have been developed in my lab using these skills of making PCBs. And we will see how interesting electronic circuits can be fabricated. Then in the second half of today, we are going to start learning how to use the KiCad program. KiCad is an open source program which runs on all the popular platforms such as Windows PC or Mac OS or on Linux platform, and this open source software can be downloaded. And in the first segment, we are going to teach how to use the KiCad program to enter the electronic schematic. It has a lot of elements. For example, all the electronic symbols, how to manage them, how to import them whenever you are creating a new symbol, how to import that into the KiCad software, and then how to create a schematic. From the schematic, we are going to come tomorrow. We are going to deal with taking the schematic as an entry point, and then how to lay out the board for the various components that form that schematic. Now, that requires you to understand the physical dimensions and placing the components appropriately on the printed circuit board, or on this circuit board that you are going to build, and then designing the PCB and then laying it out so that all the connections are made in a appropriate manner. Sometimes it may happen that all the connections cannot be accommodated on a single side, and therefore we have to go in for jumpers. Or if it is possible, we can even we'll discuss how to create a double-sided PCB. Although in this program we are going to deal with only single-sided PCB with a couple of jumpers. Now, once you have learned how to lay out the PCB, then we come to the actual aspect of transferring the layout to the actual fabrication. And it has these elements that first you have to ensure that your layout is appropriate. Then you take a printout of that on a laser printer. Once you take and you need a special paper for that. It is easily available, called photo paper. Once you take the printout, then you cut the layout according to the dimension of that PCB. On the parallelly, you have to prepare the PCB, because the PCB consists of a copper foil pasted on a substrate. Usually we are going to use what is called as FR4 type of substrate, fire resistant type 4. This is made out of glass epoxy, and you cut that PCB of appropriate size, and because the copper may be oxidized or it may have dirt on it, then you have to clean it. For that, we can first of all wash it with detergent and water, and then use a sandpaper to ensure that there is no grease or dust on the PCB. Then what you are going to do is, this printout that you have taken and you cut at the boundary, you are going to invert on the PCB on the copper side, and using a regular press, you are going to press the paper onto the copper substrate, and do it for about 5 minutes so that the entire printout is stuck to the copper. Once you have ensured that the paper has stuck well to the PCB material, then you are going to dip it in water and gently rub the paper and remove the paper, so that only the printout will be left on the copper substrate. Once that is there, you inspect the transfer. This is, by the way, this method is called toner transfer method, because the printout has been transferred on the PCB substrate. Then, to ensure that there are no shorts, you are going to take a needle kind of object and remove any paper which may still be stuck, or any shorts that may have happened because of this paper sticking between two parts of the PCB. Once this is done, then you are going to dip this copper board, PCB board, into a ferric chloride solution, and agitate it so that a reaction takes place and the exposed copper is dissolved in the ferric chloride. Once that happens, we are going to take it out of the substrate, out of the solution, and thoroughly wash it in running water. And then once we ensure that all the exposed copper has been removed, then we are going to clean it, and then using the sandpaper, rub the print which has been stuck on the copper side. And when you remove it, you will find that the copper tracks and pads appear underneath, and this is your PCB. Now components are of two types, as we will discuss, that some components require you to drill hole in the PCB, and some components are soldered on the PCB itself. They are called surface mount device components. And in our PCB we are going to use both types of components, through hole component also, and few of the components are surface mount components. So we are going to, once this PCB is etched, as this process is called, we are going to drill holes onto the PCB in our drilling machine, and then we are ready to solder. But before we do that, if we leave the copper as it is going to get exposed to oxygen, to the environment, and will get oxidized. So we need to spray acrylic spray on the PCB so as to protect the copper so that it doesn't oxidize quickly. We do that, we wait for it to dry out, and then you are ready to solder. For that, you have to take a circuit diagram, print out, keep it in front of you, keep the layout in front of you, so that you know that you are positioning the right component at the right place on the PCB. Then you need either a solder iron or a solder station. We recommend that you have a solder station, because then you have a good control on the temperature of the soldering tip, and use good quality soldering material. These days we don't need any flux, because the soldering wire itself is impregnated with flux inside. And then you should have good lighting so that you place the component appropriately, correctly on the pads or holes, insert it, and then solder. Once you do that, make sure, using a microscope or a magnifying glass, make sure that there are no shorts, and then you are ready to test. We'll apply power to the PCB, and then we'll ensure that the PCB is functioning according to the objective that it was designed for. So this is the coverage that we are going to have in the next 3 days, and I hope you are all going to enjoy this process. I hope you practice it also at home, so that not just one PCB, you go back to your college and design more PCBs and fabricate them, so that you are able to, when the opportunity comes, you are able to teach it to your students in a very effective fashion, because this is a very enabling skill. Because being able to make a PCB will enable you to design circuits, and then create experiments and use this process in doing interesting projects that you may have in your mind. To give you example, we are going to show you this process, so that this process you can refer to anytime. This video you can refer to anytime you have any doubt about the entire PCB fabricating approach. So we are going to show you how to make a PCB before we start doing it.
What is a PCB? A printed circuit board is a medium used to connect electronic components to one another in a controlled manner. It takes the form of a laminated sandwich structure of conductive and insulating layers. Each of the conductive layers is designed with an artwork pattern of traces, planes, and other features etched from one or more sheet layers of copper laminated onto and or between sheet layers of a non-conductive substrate. Why PCB is used? Printed circuit boards provide mechanical support for electronic components so that a device can be mounted in an enclosure. A printed circuit board design must include a specific set of steps that align with the manufacturing process, integrated circuit packaging, and the structure of the bare circuit board. Steps involved in PCB fabrication: printing of layout, copper clad cutting, sanding, pressing, removal of paper and needling, etching, scrubbing, acrylic spray, drilling, soldering. Step 1. Printing of layout. The first step involves printing the circuit layout onto a special transfer paper, photo paper, using a laser printer. The layout represents the copper traces, pads, and other components' locations. Step 2. Copper clad cutting. A copper-clad laminate sheet is cut to the desired size, matching the dimensions of the PCB design. The cutting can be done in two ways, using a CNC machine or manually using a hacksaw. Step 3. Sanding. The copper-clad board surface is sanded lightly to remove any oxidation or contaminants, ensuring better adhesion of the toner during the transfer process. Step 4. Pressing. The transfer paper with the printed circuit layout is placed onto the copper-clad board. Then the paper is sandwiched between iron and copper cladding, applying pressure and heat to transfer the toner from the paper to the copper surface. Step 5. Removal of paper. After pressing, the transfer paper is carefully removed, leaving behind the toner traces adhered to the copper. Needle-like tools may be used to touch up and refine the toner traces and pads. Step 6. Etching. The exposed copper not protected by the toner is etched away using a chemical solution, ferric chloride solution, leaving behind the circuit traces and pads. This creates the conductive pathways that connect the components on the PCB. The PCB is then washed to remove the extra ferric chloride solution. Step 7. Scrubbing. The remaining toner is removed from the surface of the PCB using an abrasive scrubbing process. This ensures that the copper traces are clean and ready for further processing. Step 8. Conformal spray. A conformal coating may be applied to protect the copper traces from oxidation and environmental factors. Step 9. Drilling. Holes are drilled into the PCB to accommodate component leads and mounting screws. These holes are strategically placed according to the design's requirements. Step 10. Soldering. The final step involves soldering electronic components onto the PCB. These components are placed in their designated positions, and their leads are soldered to the copper pads, establishing the electrical connections between the components and the circuit traces. This is the final PCB made in this video tutorial, known as the CPO, or Code Practice Oscillator, which can be used to practice Morse code.